Hey, this is our third video, and these are the beginning equations. We're going to start getting into calculating how we figure out how to design the car. And there is a mathematical basis to doing this, and that's what we're going to start with. Now, it can be daunting. There's a lot of things that go into it, but we're going to start simple, real simple formulas and calculations, basic general assumptions, things that are easy to work through. And we're going to help you learn how to design the car and how we made the decisions we made. Now, first off, in this initial design, we have to have some assumptions that we're going to make and some basic parameters. Now, I'm going to start off with saying for this exercise that we're going to have a max power input of 1200 watts per hour from our panel. The panels at their peak efficiency, peak performance, can only produce 1200 watts an hour. That's what we're going to say. Now, during the race, we're assuming it's a track race because those are conditions we can estimate, control. We know what they are. We know the whole situation there. During the track race, we have 21 hours of time that the car is able to charge its batteries. Now, that 21 hours is done in the Monday, Tuesday, and Wednesday evenings after the race, Monday through Thursday during lunch from 12 to 2, and Tuesday, Wednesday, and Thursday in the morning from 6:30 until 9 when it's racing. There's 21 hours there that we're able to charge the car. And because we can face the panels directly at the sun, but there's going to be little things that misalign it or cause it to not be max efficient, we can assume that we will be charging at 90% efficiency. So we'll get 90% of that 1200 watts every hour. So if we multiply 21 hours times 1200 times 90%, that would give us a total of 22,680 watts during the charging time. We would be collecting over that 21 hours. While the car's driving, on the other hand, it's not in a perfect alignment. It's out there, it's moving around, clouds, you can't avoid things. So we say that it's 70%. And there's 23 hours of racing, actually. It's 9 to noon every day, and then 2 to 5 on the first 3 days, and then 2 to 4 on the last day. So it's 23 hours of driving. That gives you 19,320 watts. You take those two numbers and add them together, it gives you a total of 42,000 watts of power that we will be collecting in from the solar array the entire race that's available for use. We have 42,000 watts available for use over the 23 hours of driving. So we divide that by 42,000 by 23, and that tells us that we have a max input of 1,820 watts an hour. So the power the car uses cannot exceed 1,820 watts. If it does, we're going to run out of power and we'll finish the race too early. If we use less than that, we've got fuel left over, and you don't get any points for excess fuel, for having energy left in the batteries at the end of the race. You want to use everything you can. So we're going to try to get to that 1,820 as good as we can. That's our goal. Now again, these are all our initial estimates. We will modify this more. There's some things we haven't taken into account right now. Don't worry about those. We're just starting. So we need to look at the three factors that affect that power that is consuming that 1,820 watts. There are three main things affecting it: aerodynamic drag, rolling resistance drag, and mechanical efficiencies. And we're going to talk about each of those specifically, but it goes in this formula: aero drag plus rolling resistance drag divided by the motor efficiency. And that will tell you how much power you're consuming. And that number can't be greater than 1,820. So let's talk about mechanical efficiency, the denominator. These are things, energy that's lost because of the shocks moving up and down, the steering being misaligned, steering in the car, the steering misalignment, the drivetrain, the motor, the brakes. All these little things take away power that isn't transferred to motion, but actually is stopping the car. So we say that the car, and for us, we're going to make the general assumption right now that our car is 85% efficient. We're going to leave it at a constant until we can test it out. We're going to make the assumption that we're going to design the car and build the car as well as we possibly can and get everything as aligned and as tweaked as perfect as we can, and perfect bearings, perfect everything, as good as it can be to have the most efficiency. Because a lot of that just is based on effort and the time you put into it. And so we're going to make the assumption we're going to put in all the effort we need and all the time we need to do it right. So that's going to be a constant 85%. Now let's talk about rolling resistance. Rolling resistance is a function of your drag coefficient the weight of the car, and the speed of the car. And you can see this formula here. It's 0.199 times the coefficient of rolling resistance drag times 1 plus velocity over 100 times the weight times the velocity. Now the velocity is in miles per hour and your weight is in pounds. If you go in and put the numbers in, I want you to check my math, but we're going to assume the tires have a coefficient, rolling resistance coefficient of 0.01. We're going to our target velocity average is 35 miles per hour, and our target weight, the car's target weight is 600. But remember, we got a driver in there, so we're going to add 150 pounds for that. So our target weight is 750 pounds. And if you go in, you multiply all that out, it comes out to about 705 watts. That's the power that the car's consuming from rolling resistance. Now, we're going to assume for the moment that once we pick tires, that coefficient of drag on the rolling resistance drag, that's a constant. We're going to assume that for now. We're going to assume that we're going to get the weight of the car under 600 pounds, so the total weight, gross weight, is 750 pounds. We're going to assume we're doing everything right to get that 750, and we're going to assume we're going to average 350 pounds, or 35 miles an hour. So these are all constants. So this is going to give us a constant 705 watts every hour that we're using from rolling resistance. Now, aerodynamics. Aerodynamic drag is a function of air density, the velocity of the car, the frontal area of the car, and the coefficient of aerodynamic drag. And you can see this formula to the right. It's your power from aerodynamics is 0.0523 times the cube of velocity. Oh wow, you cube the velocity. So the faster you go, the worse the power needs are badly. It's cubed. Times a function called AC sub d. That's area times the coefficient of drag. And we call that our drag area. And that's the name of that formula. AC sub d is your drag area. And so we know our velocity is 35 miles an hour. We're going to make that a constant. But we don't know anything about the frontal area or the coefficient of drag. Those are going to be the variables that we don't mess with. And we're going to assume air density is a constant too, because we know it's July, so we're going to assume this number here. Now, so we can solve in here and reduce this formula a little bit. So we can put in 35 miles an hour, cube it, multiply it by 0.0523, and that would give us a function of the power is 2,243 times our drag area. That gives us down to one variable that we need. It's going to reduce this formula to one variable. We're going to first work on our design, getting the frontal area and the coefficient of drag down to under what we need for the car to perform. So, to figure out the drag area, what we're solving for, we got one variable we're solving for, because we know our total power. If we go back to our original formula, we know total power, we know the motor efficiency, we know rolling resistance drag, and we know part of aero drag. Aero drag is the only thing we don't know specifically. We know all of it but one thing, the drag area. So we come in here and we want to calculate the area drag of the car, or the drag area of it, and it's 1,820 watts equals 705 watts plus a function 2,243 times the drag area divided by 0.85, that 85% mechanical efficiency. And if you solve for your drag area, then you get a 0.375. And that's saying that what that's telling you is that our car, the design of the car, the drag area has to be less than 0.375. And if we can get that in, which is the frontal area of the car and the drag coefficient, if we can get that in under that number, we should have enough power to be able to run the whole race at 35 miles an hour. If everything else holds true, that we get the car's weight down, that we build it all with the right efficiencies and all of those things. So this is your first starting calculation. And this is the number that we're looking for. Now, I did do one thing though. I made an assumption that's not accurate to what our car is going to be. Our car is actually going to be powering 1,440 watts on its solar array right now. So I want you to go in, and this is your homework assignment. You're going to upload it to the Dropbox. You're going to rework this formula and calculate it for the actual number of 1,440 watts of power. So you need to figure out how much power would our array be generating over the course of the whole race. So how much power would we have per hour to use for the race? And then what would the drag area need to be? Would max drag area be? And that's what you're going to submit into the Dropbox after this. And then from here, we'll move on to the next step. So go ahead and do that and have a good day.